It was the mid-1960s. The world was in upheaval, but in the quiet halls of Cambridge University, a different kind of revolution was brewing. It was a revolution in our understanding of gravity and the cosmos. A young graduate student named Stephen Hawking was there, already battling the early stages of his debilitating illness, but with a mind that was fiercely sharp. And elsewhere, a brilliant mathematical physicist named Roger Penrose was thinking about stars. Not just any stars, but massive ones, the kind that live fast and die hard. Einstein's theory of general relativity, published back in 1915, was the best description of gravity anyone had. It said that massive objects warp the fabric of space-time, but the full implications of this warping were still being worked out. In 1965, Penrose published a groundbreaking paper. He used new mathematical tools to prove something startling. He showed that when a massive enough star runs out of fuel and collapses under its own gravity, nothing can stop it. The collapse is unstoppable. It will inevitably form a region from which not even light can escape, a black hole. But Penrose's work went deeper. He proved that inside this black hole, the collapse must continue until all the star's matter is crushed into an infinitely small, infinitely dense point. He called this a singularity. It wasn't just a weird possibility. According to the mathematics of general relativity, it was a certainty. A few years later, between 1966 and 1970, Hawking took Penrose's ideas and applied them to the entire universe. He showed that if you run the clock backward on our expanding cosmos, you also end up at a singularity, the Big Bang. Together, the Penrose-Hawking singularity theorems were a triumph. They were beautiful, elegant proofs. But they also presented a huge problem. A singularity is a point where the density is infinite. The curvature of space-time is infinite. The laws of physics as we know them just stop working. They break down completely. It's a place where the equations return answers of infinity, which is another way of saying, we have no idea what's going on. For the past 50 years, this has been one of the biggest mysteries in science. General relativity predicts this point of breakdown, but it can't describe it. So what is actually there? Is it really a point of infinite nothingness? Or is it something else entirely, something our current physics just isn't equipped to understand? The quest to answer that question has led to some of the most bizarre and mind-bending ideas in all of science. Number 21. We simply do not know. The Planck length is about 1.6 x 10 raised to the power of 35 meters. It is the shortest possible length that makes sense in physics. Any smaller and the concepts of length and distance lose their meaning. The Planck time is the time it takes light to travel that distance, a stunningly small 10 raised to the power of 43 seconds. The mass of the supermassive black hole at the center of our galaxy, Sagittarius A, is about 4.3 million times the mass of our sun. This is the most honest place to start. Before we explore any of the wild theories, we have to admit the simplest truth. We do not know what is at the center of a black hole. We have no direct way to look. We can't send a probe. Any information from inside is, by definition, trapped. What we have are two incredibly successful theories of the universe. One is general relativity, which describes gravity and the large-scale structure of the cosmos. The other is quantum mechanics, which describes the bizarre world of particles and forces on the smallest scales. The problem is, these two theories do not agree. General relativity works with a smooth, continuous fabric of space-time. It's like a rubber sheet. Quantum mechanics describes a world that is chunky, probabilistic, and weird. It's made of discrete packets called quanta. For most of the universe, this isn't a problem. You can use general relativity to describe a planet's orbit and quantum mechanics to describe how a laser works. They stay in their own lanes. But a black hole singularity is the one place in the modern universe where their lanes cross. It is both incredibly massive, the domain of general relativity, and incredibly small, the domain of quantum mechanics. To understand it, we need a single theory that can handle both gravity and the quantum world. We need a theory of quantum gravity. We don't have one. So every theory that follows is an attempt to guess what that future theory of quantum gravity will say. They are all educated guesses based on different approaches to unifying these two great pillars of modern physics. Some come from string theory, some come from loop quantum gravity, some are even more exotic. But none of them are proven. They are all attempts to fill in the biggest blank spot on the map of physics. It's a place where our best science tells us that our science fails, and acknowledging that ignorance is the first, most crucial step. It is the foundation upon which all the speculation is built. It is the honest answer. We just don't know. Number 20, it's a source of the universe's expansion. Dark energy is thought to make up about 68% of the total energy content of the universe. The vacuum energy predicted by quantum field theory is about 120 orders of magnitude larger than the value we observe in cosmology, a discrepancy called the cosmological constant problem. A 2019 study by astronomers at the University of Hawaii suggested that black holes could be the source of dark energy. They found that the mass of black holes in certain galaxies grew more than expected, consistent with them containing vacuum energy. Here is a strange idea that connects the biggest things in the universe with the smallest. What if the singularity isn't a point of crushed matter, but a core of dark energy? This is the central idea behind a model called GEODES, which stands for Generic Objects of Dark Energy. In this view, when a star collapses, it doesn't form a singularity at all. Instead, the intense pressure and gravity cause the matter to undergo a kind of phase transition, turning it into vacuum energy, the same stuff we call dark energy. So, instead of a tiny point, the center of a black hole would be a sphere of this exotic energy. It would still be hidden behind an event horizon, so from the outside it would look and act just like a regular black hole. It would have the same powerful gravity, but on the inside it would be completely different. There would be no infinity, no point where physics breaks down. There would just be a core of pure vacuum energy. This idea does something remarkable. It might solve two huge cosmological mysteries at once. First, it solves the singularity problem, but second, it provides a source for dark energy. We see the universe's expansion accelerating, and we attribute this to dark energy, but we don't know where it comes from. The geode model suggests that black holes are the factories. As they form from stars and gobble up more matter, they are constantly converting that matter into new dark energy. This means that the total amount of dark energy in the universe is not constant. It's growing over time as more black holes form and grow. This is a testable prediction. By looking at the history of cosmic expansion and the population of black holes over billions of years, we could see if this model matches reality. It's a wild thought. The black holes that seem to be cosmic vacuum cleaners, sucking everything in, could actually be the engines pushing everything apart on the largest scales. The ultimate destroyers could be the ultimate creators of the universe's future. Number 19, it's the ultimate computer. The Bekenstein bound, formulated by Jacob Bekenstein in 1981, sets the absolute upper limit on how much information can be stored in a given region of space with a finite amount of energy. A black hole is the most information-dense object allowed by this bound. A hypothetical computer the size of a single sugar cube, if it were a black hole, could store more information than all the data currently on Earth. The theoretical physicist Seth Lloyd calculated that a 1 kilogram black hole could perform 10 raised to the power of 50 operations per second. This theory takes the phrase, "it from bit" seriously. Proposed by the physicist John Archibald Wheeler, this is the idea that the universe is, at its most fundamental level, made of information. Every particle, every force, every interaction is just a state of information being processed. If that's true, then what is the most powerful computer you could possibly build? The answer, according to some physicists, is a black hole. A black hole is the densest possible storage medium in the universe. When something falls into a black hole, its information isn't destroyed. It's stored, packed as tightly as the laws of physics will allow. The singularity, in this view, isn't a point of infinite density, but a point of maximum computation. It is a processor of unimaginable power. What is it computing? That's the big question. Perhaps it's running a simulation. A simulation of what? Maybe of the very laws of physics that govern it. Or maybe it's processing the history of every particle that ever fell into it, trying to calculate some final, ultimate state. The energy and matter that fall in are the fuel and the input data. The singularity is the central processing unit. The event horizon is like the firewall, protecting the calculation. This idea connects deeply with the holographic principle, which suggests all the information in a volume of space can be encoded on its surface. For a black hole, all the information about its three-dimensional interior could be encoded on its two-dimensional event horizon. The singularity then becomes the central hub where this information is processed and manipulated. It flips our view of a black hole on its head. It's not a dead end for matter and energy. It's the most active and efficient place in the cosmos. It's a natural computer that emerged from the laws of physics, performing calculations on a scale that we can barely comprehend. The universe might not just be like a computer, it might actually be one, and black holes are its most powerful processors. Number 18, it's the end of time. For an observer far away from a black hole, it would take an infinite amount of time to watch an object actually cross the event horizon. This is due to gravitational time dilation. An astronaut falling into a stellar mass black hole would be torn apart by tidal forces, a process called spaghettification, long before reaching the singularity. For a supermassive black hole, the tidal forces at the event horizon are much weaker, and an astronaut could cross it without noticing anything immediately wrong. Let's think about time. We experience it as a constant flow, always moving forward. But Einstein showed us that time is not absolute, it's relative. Gravity warps time. The stronger the gravity, the slower time flows. This effect is real and measurable. The GPS satellites in orbit around Earth have to constantly adjust their clocks because time runs slightly faster for them than it does for us on the surface. Now imagine a black hole. Its gravity is the most extreme in the universe. As you approach the event horizon, time dilation becomes more and more severe. For someone watching you from, a safe distance, your clock would appear to tick slower and slower. As you reach the event horizon, your clock, from their perspective, would seem to stop completely. You would appear frozen in time for all eternity. But what about your experience? For you, falling in, time would seem to pass normally. You would cross the event horizon without any fanfare. But once inside, the nature of space-time changes dramatically. The direction toward the singularity, the center, is no longer a direction in space. It becomes a direction in time, it becomes the future. Just as you cannot stop moving into your future right now, an object inside a black hole cannot stop moving toward the singularity. There is no other direction to go. All possible paths lead there. The singularity is not a place you can go to. It is an event in time that you must meet. It is the end of your own personal timeline. So, what is the singularity? It's the end of time itself. For any object or person who falls in, the singularity represents the final moment of their existence. It's not a place made of crushed matter, but a moment in time beyond which there are no more moments. Space-time, as we understand it, ceases to exist. It's a temporal dead end. The rules that govern cause and effect before and after break down. It's the ultimate destination, not in space, but in time. Number 17, it's an intersection with another dimension. String theory, a leading candidate for a theory of everything, requires the existence of extra spatial dimensions to be mathematically consistent. Most versions of the theory predict 10 or 11 dimensions in total 9 or 10 of space, 1 of time. In brain cosmology, our entire 4-dimensional universe, 3 space plus 1 time, is a brain floating in a higher dimensional space called the bulk. Our universe feels 3-dimensional. We have length, width, and height. But what if that's not the whole story? What if our entire universe is just a thin membrane, a brain, floating in a much larger, higher dimensional space? This idea comes from string theory and is known as brain world cosmology. In this scenario, most of the particles and forces of our universe are stuck to our brain. We can't move off it. We can't perceive the extra dimensions directly, but there is one force that might be different gravity. Gravity in this model is not confined to our brain. It can leak out into the higher dimensional bulk. This could explain why gravity is so much weaker than the other fundamental forces like electromagnetism. It's because its influence is diluted by spreading out into these extra dimensions. Now, think about a black hole. A black hole is pure gravity. It's a place where gravity is so strong it has overwhelmed everything else. So what if a black hole in our 3D universe is actually a manifestation of a higher dimensional object? What if the singularity is not a point in our space, but a point where our brain is being poked or intersected by something from the bulk? In this view, the black hole is a window into these extra dimensions. The intense gravity we feel is the effect of a massive object that exists primarily in the bulk, just barely touching our universe. The singularity is the point of contact. It's not a crushed star in our dimensions, but something far stranger. This could also explain some mysteries about black holes. For instance, when a black hole evaporates via Hawking radiation, information about what fell in seems to be lost, which violates a key principle of quantum mechanics. But if the information isn't lost but has just leaked off our brain into the higher dimensional bulk, the problem might be solved. The singularity then is not an endpoint. It's a gateway, a portal to a larger unseen reality that our senses and experiments are blind to. Number 16, space-time is undergoing a phase change. Water can exist as a solid ice, a liquid water, or a gas steam. These are different phases of the same substance, H2O. The transition between them is a phase transition. In 2014, physicists argued that space-time itself could undergo a phase transition inside a black hole, similar to how liquid water turns to ice under pressure. This idea arises from treating space-time as being composed of fundamental discrete atoms of space-time. We are used to the idea of phase transitions. Water freezes into ice, steam condenses into water. These are changes in the state of a substance, usually caused by changes in temperature or pressure. The underlying molecules are the same, but their arrangement and behavior change dramatically. Ice is rigid and crystalline, water is a fluid, steam is a diffuse gas. What if space-time itself can undergo a phase transition? Normally we think of space-time as a smooth, continuous background, but many theories of quantum gravity suggest that space-time is not fundamental. It's an emergent property built for more basic, discrete components like atoms of space-time. If this is true, then just like water, space-time could have different phases. The inside of a black hole is a place of extreme conditions. The gravitational pressure is unimaginable, so what if the singularity is not a point of infinite density, but a region where space-time itself has undergone a phase transition? The atoms of space-time, which normally give rise to the smooth fabric we experience, get squeezed so hard that they rearrange themselves into a new exotic phase. What would this new phase be like? We don't know for sure. It might be a state where the distinction between space and time blurs or disappears entirely. It might be a kind of space-time solid, a crystalline structure at the quantum level. It would be a region governed by completely different physical laws. There would be no singularity, no infinity. The collapse of the star would be halted when the matter reaches this new phase, much like water can't be compressed beyond a certain point once it turns to ice. This theory replaces the breakdown of physics at the singularity with the emergence of new physics. The singularity is not an end, but a transformation. It's a place where the very fabric of reality changes its state, from the familiar liquid space-time we live in to some kind of bizarre quantum ice at the heart of the black hole. Number 15, all the information is on a wall of fire. The black hole information paradox was first identified by Stephen Hawking in the mid-1970s. It points out that Hawking radiation seems to destroy the quantum information of things that fall into a black hole, which violates a fundamental law of physics. The firewall paradox was proposed in 2012 by physicists Joseph Polchinski, Ahmed Almheri, Donald Marolf, and James Sully. It was an attempt to resolve some deep inconsistencies in our understanding of black holes. This is one of the most controversial and unsettling ideas about black holes. It comes from trying to solve the black hole information paradox. The paradox is this: quantum mechanics says information can never be destroyed. If you burn a book, the information in it isn't gone. It's just scrambled into the positions and energies of the ash, smoke, and heat. In principle, you could reverse the process and reconstruct the book. But Stephen Hawking showed that black holes evaporate over very long timescales, emitting what's called Hawking radiation. This radiation seems to be random and thermal. It doesn't seem to contain any information about what fell into the black hole. So when the black hole completely evaporates, where does the information go? It seems to be destroyed forever. Physicists have struggled with this for decades. One proposed solution led to the firewall theory. The idea is that information doesn't actually make it inside the black hole. Instead, as the black hole ages, a high energy region, a firewall forms at or very near the event horizon. What does this mean for someone falling in? According to Einstein's general relativity, crossing the event horizon should be uneventful. It's a point of no return, but it's not a physical barrier. The firewall theory says Einstein is wrong about this one detail. When you reach the event horizon, you don't glide through. You hit a wall of super hot, high energy particles and are instantly incinerated. Your information doesn't fall into the black hole. It gets absorbed by the firewall and is then re-radiated back out as part of the Hawking radiation, solving the information paradox. But this creates a new, massive problem. It violates Einstein's equivalence principle, a cornerstone of general relativity, which states that the laws of physics should be the same for all observers in free fall. For the astronaut falling in, there should be nothing special about the event horizon. A firewall is very special. It's a violent physical barrier. This theory, forces a choice between two pillars of modern physics: quantum mechanics or general relativity. The firewall concept suggests that at the edge of a black hole, one of them must be wrong. The singularity inside becomes irrelevant because nothing can ever reach it. The real drama happens at the door. Number 14, spacetime is woven from unbreakable loops. Loop quantum gravity, LQG, is a competing theory to string theory. It does not require extra dimensions. In LQG, the smallest possible unit of area is the Planck area, about 10 raised to the power of 70 square meters. You cannot have a surface smaller than this. The theory predicts that the Big Bang was actually a big bounce, where a previous contracting universe reached a point of maximum density and then bounced back to form our expanding universe. This theory comes from a different approach to quantum gravity called loop quantum gravity, or LQG. Unlike string theory, LQG doesn't try to unify all forces. It focuses only on quantizing gravity. It takes Einstein's idea that gravity is the geometry of spacetime and applies quantum rules to it. The result is a picture of space-time that is not smooth and continuous, but granular. It's made of tiny, indivisible loops, or quanta of space. Think of it like a piece of fabric. From a distance, it looks smooth, but up close, you see it's woven from individual threads. LQG says space-time is like that. This has a profound consequence for the singularity. In general relativity, you can keep squeezing matter into a smaller and smaller volume, all the way down to a point of zero volume and infinite density. But in LQG, you can't. There is a smallest possible volume, a fundamental grain of space. You can't squeeze matter any smaller than that. So what happens when a star collapses? The matter gets crushed, and the density becomes enormous, far beyond anything we can imagine. But it doesn't become infinite, like when it reaches the maximum possible density allowed by the quantum structure of spacetime. A new force emerges. It's a repulsive force born from the quantum nature of geometry itself. You can think of it as spacetime pushing back. It will not allow itself to be compressed into nothingness. This repulsive force halts the collapse. The infalling matter then bounces. The singularity is replaced by this Planck density core. The matter is in a state called a polymer, a chain of space-time quanta. This core is incredibly small and dense, but it's finite. There is no infinity, there is no breakdown of physics. What happens after the bounce? The theory suggests that the black hole eventually transitions into a white hole. A white hole is the time-reversed version of a black hole, an object from which things can only fly out. So, in the far, far future, the matter that fell into the black hole could be spewed back out into the universe. The singularity is not a dead end, but a cosmic turnaround point. Number 13, the universe hides its own failures. The cosmic censorship hypothesis was first proposed by Roger Penrose in 1969. There are two versions, the weak and the strong. The weak version states that any singularity must be hidden behind an event horizon. The strong version states that no observer, even one inside a black hole, can ever see a singularity. To date, neither version has been mathematically proven for all cases, but there is substantial evidence for them. This idea is less about what the singularity is and more about where it is. It's a principle called the cosmic censorship hypothesis. Put simply, the hypothesis says that the universe abhors a naked singularity. A naked singularity is a singularity that is not hidden behind an event horizon. It would be a point of infinite density and infinite spacetime curvature that is visible to the outside universe. If a naked singularity existed, it would be a disaster for physics. Since the laws of physics break down at a singularity, a naked one could spew out random, unpredictable effects into the rest of the universe. Anything could come out of it. Cause and effect would break down. The predictive power of science would be lost. You could never be sure what might happen next, because a naked singularity could arbitrarily change the rules. The cosmic censorship hypothesis proposed by Roger Penrose is the idea that nature forbids this. It's a conjecture that says whenever a singularity forms in the universe through a realistic process like stellar collapse, an event horizon will always form around it to censor it, to hide it from view. The black hole's event horizon acts as a cosmic quarantine, protecting the rest of the universe from the lawlessness of the singularity within. In this view, the singularity might well be a point of infinite density where physics breaks down. But it doesn't matter because it's safely locked away. The universe has a built-in safety mechanism. Whatever happens at the center of a black hole, it stays in the black hole. We are shielded from the breakdown of our physical laws. So, what's inside a black hole? A true singularity, a point where our theories fail. But the universe, in its wisdom, has drawn a curtain around it, ensuring that its failure remains its own private problem, not ours. The theory is an admission of defeat, but a contained one. We don't know what's there, but nature ensures that we never have to deal with the consequences of not knowing. Number 12, it's a vortex in a space-time superfluid. A superfluid is a state of matter that has zero viscosity. If you stir a cup of superfluid, it will continue to spin forever without slowing down. Helium-4 becomes a superfluid when cooled to below 2.17 Kelvin 270.98 Celsius. In 2000, physicist Powell Mazur proposed the Gravastar model, which involves a core of exotic matter that acts like a Bose-Einstein condensate. What if space-time isn't the fundamental entity we think it is? What if it's an emergent phenomenon, like the way the fluid behavior of water emerges from the interactions of countless individual H2O molecules? This is the idea behind the theory of spacetime as a kind of fluid. At our normal low-energy scales, it behaves like a perfect, smooth fluid. But under extreme conditions, its underlying atomic nature might be revealed. Following this analogy, a black hole could be seen as a kind of vortex or whirlpool in this space-time fluid. And the singularity at its center, it might not be a point of infinite density, but a region where the fluid has changed its properties, much like the eye of a storm. One specific version of this idea treats space-time as a superfluid. A superfluid is a quantum fluid with zero viscosity. It flows without any friction or loss of energy. This is a real observed phenomenon in labs at extremely low temperatures. If spacetime is a superfluid, then a black hole is a region where this fluid is flowing inward faster than the speed of light. The event horizon is the point where the fluid's speed hits the speed of light. At the very center, the singularity is replaced by something else. It could be a phase transition boundary where the superfluid spacetime turns into some other state, or it could be a defect, a tiny hole in the superfluid, similar to the tiny empty core of a bathtub drain vortex. The laws of physics wouldn't break down. Instead, the behavior of the underlying atoms of spacetime would create a stable, though exotic, structure at the center. This approach allows physicists to study black holes using the well-understood mathematics of fluid dynamics. They can create dumb holes, which are acoustic analogs of black holes in laboratory superfluids. By studying how sound waves get trapped in these lab-created vortices, they can gain insights into how real black holes might behave. It's a radical idea the universe's most mysterious objects might be understood by looking at the behavior of supercold liquid helium in a lab. Number 11. The interior is a two-dimensional hologram. The holographic principle was first proposed by Gerard Hooft in the early 1990s, and was given a more precise string theory interpretation by Leonard Susskind in 1995. The theoretical maximum amount of information that can be stored in the entire observable universe is estimated to be around 10 raised to the power of 122 bits. According to the holographic principle, all of that information could be encoded on a two-dimensional surface enclosing the universe. This is one of the most mind-bending ideas to come out of modern physics. It's called the holographic principle. We are used to holograms as two-dimensional surfaces, like on a credit card, that can store the information for a three-dimensional image. The holographic principle suggests that the entire universe might work this way. It proposes that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. What does this have to do with black holes? Black holes are actually what led to this idea. Jacob Bekenstein and Stephen Hawking discovered something strange about black holes. The amount of information a black hole can hold its entropy is not proportional to its volume, as you might expect. It's proportional to the surface area of its event horizon. It's as if all the information about the black hole's three-dimensional interior is somehow smeared out and encoded on its two-dimensional surface. The holographic principle takes this and runs with it. If this is true, then maybe the three-dimensional interior of the black hole isn't even real in the way we think. Maybe the only real thing is the two-dimensional event horizon, which contains all the information. The three-dimensional space inside, including the singularity, could be a kind of holographic projection. It's a description, an image generated by the real physics happening on the 2D surface. In this view, there is no singularity inside the black hole. The concept of a place inside the black hole is a flawed illusion. When an object falls into a black hole, its constituent information gets scrambled and stored on the event horizon. The experience of falling toward a central point of infinite density is just part of the projection. The reality is a complex quantum system living on the surface. This idea radically changes our concept of space and locality. It suggests that our three-dimensional world could be a holographic projection of a two-dimensional reality. And black holes are the places where this principle is most clearly at work. The singularity isn't a point in space. It's an artifact of a flawed three-dimensional description of a fundamentally two-dimensional system. Number 10, it's a sea of space-time foam. The concept of quantum foam was first proposed by John Archibald Wheeler in 1955. At the Planck scale 10 raised to the power of 35 meters, the Heisenberg uncertainty principle would allow for enormous fluctuations in energy and momentum. These energy fluctuations would be so large that they would warp and twists the fabric of space-time, creating a chaotic, bubbling foam of tiny wormholes and short-lived virtual black holes. Quantum mechanics tells us that on the smallest scales, the universe is a chaotic and uncertain place. There is a principle called the Heisenberg uncertainty principle, which says you can't know both the position and the momentum of a particle with perfect accuracy. This uncertainty also applies to energy and time. For very short periods, energy can fluctuate wildly. It can be borrowed from the vacuum as long as it's pied back quickly. This leads to a strange picture of empty space. On the quantum level, it's not empty at all. It's a roiling, bubbling soup of virtual particles popping in and out of existence. And physicist John Wheeler took this idea and applied it to space-time itself. He suggested that on the tiniest possible scale, the Planck scale, the geometry of space-time would also be fluctuating wildly. He called this quantum foam or space-time foam. In this view, space-time at its most fundamental level is not smooth. It's a chaotic mess of tiny, constantly changing shapes. Tiny wormholes and miniature black holes might be popping in and out of existence in this foam, connecting different points in space and time. So, what is the singularity? It's not a single, stable point. It's a region where the density of matter has become so great that it has churned space-time into a permanent violent state of this quantum foam. The classical idea of a single, well-defined point of infinite density disappears. It's replaced by a region of maximum chaos. This region wouldn't have a specific location. It would be a probabilistic cloud of roiling geometry. Space and time would lose their familiar meaning, dissolving into this fundamental foam. There would be no single point of infinite density, but rather a region of incredibly high but finite and rapidly fluctuating energy. The laws of physics don't break down. They are just replaced by the more fundamental, chaotic laws of the quantum foam. The singularity is not a point. It's a storm at the bottom level of reality. Number 9. A geode is not what you think it is. This one is a bit of a trick, but it's an important distinction. Geode stands for generic object of dark energy. This is the model we discussed earlier, where the singularity is replaced by a core of dark energy. The idea was put forward in 2019 by Kevin Croker and Joel Weiner. The crucial part of their work is that these objects would not be distinguishable from standard black holes by observations from the outside, but their growth over cosmic time could be a signature that differentiates them. We've already touched on the idea of a geode, a generic object of dark energy. It's the theory that a black hole's singularity is replaced by a core of vacuum energy, or dark energy, but it's worth a chapter of its own to emphasize how this changes our view of black holes and their role in the universe. Normally we think of black holes as passive objects. They sit there, and if something gets too close, it falls in. They are cosmic dead ends. The geode model transforms them into active, dynamic participants in the evolution of the cosmos. In this picture, black holes are not just eaters of matter, they are producers of dark energy. Think about the life cycle of the universe. It began with the Big Bang, expanded and formed stars and galaxies. For a long time, the gravity of all this matter was slowing the expansion down. But about 5 billion years ago, something changed. The expansion started to speed up. We attribute this to dark energy, a mysterious, repulsive force that is pushing the universe apart. The geode model provides a physical source for this dark energy. The first stars formed, and the most massive ones quickly died and collapsed into the first black holes. According to the model, these black holes began converting stellar matter into dark energy. As more stars formed and died, and as galaxies merged, the population of black holes grew. They got bigger and more numerous, and as they did, they pumped more and more dark energy into the fabric of space-time. Eventually, the total amount of this black hole-produced dark energy became significant enough to overpower the collective gravity of all the matter in the universe. At that point, the cosmic expansion stopped slowing down and started accelerating. The timing in the model seems to match what we observe. This makes black holes the engines of the universe's ultimate fate. They are not just celestial tombs, they are the factories that are driving the cosmos toward a future of ever-accelerating expansion. The singularity is not a point of broken physics, but a functioning machine, a converter of matter into the very energy that shapes the destiny of the entire universe. Number 8, it's a stable, tiny remnant. The idea of black hole remnants is one possible solution to the information paradox. If a black hole evaporates completely, the information is lost. But if it evaporates down to a tiny, stable remnant about the size of a Planck length, the information could be stored inside it forever. This would mean that our universe is filled with these tiny, invisible remnants from black holes that formed and evaporated in the early universe. Let's go back to the information paradox. A black hole evaporates by emitting Hawking radiation. This radiation is thermal, meaning it seems random. It doesn't seem to carry any of the specific information about the things that fell into the black hole. If the black hole evaporates completely, that information is gone forever, which violates the laws of quantum mechanics. There are a few proposed solutions. The firewall is one. Another is the idea of a black hole remnant. The idea is that a black hole doesn't evaporate completely. The process of evaporation governed by Hawking radiation, continues for an incredibly long time. A solar mass black hole would take about 10 raised to the power of 67 years to evaporate. But as it gets smaller and smaller, quantum gravity effects would become more important. The remnant theory suggests that when the black hole shrinks down to about the Planck size 10 raised to the power of 35 meters and Planck mass about 22 micrograms, the mass of a human eyelash, the evaporation stops. What's left is a tiny stable object called a remnant. It would be a speck, far too small to ever see, but it would be incredibly dense and would contain all the information of the original massive black hole. So the singularity isn't a singularity at all. It's the final state of the collapse, this ultra-compact remnant object. It doesn't have infinite density, just the maximum possible density allowed by quantum gravity. It's a stable particle. This has a strange implication. If this theory is true, our universe could be filled with these remnants. Every black hole that has ever formed and evaporated away would have left one behind. These remnants would have mass and would interact gravitationally. Could they be a component of dark matter? Dark matter is the mysterious, invisible substance that makes up about 27% of the universe and holds galaxies together. We don't know what it is. Perhaps it's a sea of these tiny, information-rich leftovers from long-dead black holes. The singularity in this view is not a point of destruction. It's a final, stable state of matter, a tiny cosmic hard drive that preserves information for eternity. Number 7, it's a factory for new universes. The theory of eternal inflation, developed by Alan Guth and Andre Linde, suggests that our Big Bang was not a one-time event. Instead, our universe is just one bubble in a vast, eternally inflating multiverse. New bubble universes are constantly being created. Lee Smolin's theory of cosmological natural selection, proposed in 1992, suggests that new universes are born inside black holes, and the physical constants of these new universes are slightly different from the parent universe. This is perhaps the grandest idea of all. What if the singularity is not the end of everything, but the beginning of everything? What if every black hole is the seed of a new universe? This idea, known as cosmological natural selection or the fecund universes theory, was proposed by physicist Lee Smolin. It combines ideas from cosmology and biology. Here's how it works. When a massive star collapses, it forms a singularity. But according to this theory, the singularity is not a point of infinite density. Instead, the matter bounces. but it doesn't bounce back into our own universe as a white hole. Instead, the immense energy and density at the point of collapse triggers the creation of a brand new baby universe. This new universe expands from its own Big Bang, completely causally disconnected from our own. From our perspective, the black hole is just a black hole, but on the other side of the singularity, a new cosmos is born. This leads to a kind of cosmic evolution. Smolin's theory suggests that whenever a new universe is born, its fundamental constants of nature, like the strength of gravity or the mass of an electron, are slightly different, slightly mutated from the parent universe's constants. Now, think about what kind of universe would be good at reproducing. A universe that is good at making black holes. To make a lot of black holes, you need to be able to form a lot of massive stars. This requires a specific set of physical constants. If the constants were slightly different, stars might not form, or they might not be massive enough to collapse into black holes. So universes that have constants tuned for producing lots of black holes will have more offspring universes. Over countless generations of universes, a form of natural selection takes place. The universes that become common are the ones that are best at making black holes. Our universe has a set of physical constants that are exquisitely fine-tuned for the existence of stars, galaxies, and life. Why? According to this theory, it's not for us. It's because those same constants are also excellent for making lots of black holes. Here, we are just a byproduct of a cosmos that has evolved to maximize its own reproduction. The singularity is not a grave, it's a womb. Number 6, it's a bridge to somewhere else. The concept of a wormhole, a theoretical passage through space-time, emerged from the work of Albert Einstein and Nathan Rosen in 1935. They are often called Einstein-Rosen bridges. While mathematically possible under general relativity, a traversable wormhole would require exotic matter with negative energy density to hold it open. We have never observed such matter. A black hole formed from the collapse of a star would not naturally form a wormhole. This is one of the most famous ideas from science fiction, but it has its roots in real physics. It's the idea that a black hole is one end of a wormhole, a tunnel through space-time. The singularity in this case isn't a point of crushed matter, but the throat of this tunnel. If you could pass through it, you would emerge somewhere else entirely. Where is somewhere else? It could be another point in our own universe, billions of light years away. It could be another point in time, in the distant past or future. Or it could be another universe entirely, a parallel reality with its own stars and galaxies. The original version of this idea, the Einstein-Rosen bridge, connected a black hole to a white hole. A white hole is the time-reversed version of a black hole. Nothing can get in, and matter can only spew out. So you would fall into the black hole and come flying out of the white hole somewhere else. There's a huge problem with this, though. According to general relativity, these simple wormholes are not traversable. The throat of the wormhole would pinch off and collapse into a true singularity so quickly that not even a beam of light would have time to get through. Anyone or anything trying to pass through would be crushed. To get around this, you would need to prop the wormhole open with some kind of exotic matter. This isn't just matter, that's strange. It's matter with properties that seem to violate the known laws of physics, specifically matter with negative mass or negative energy density. This would create a kind of anti-gravity that would push the walls of the wormhole apart and keep it stable. We have never seen any evidence that such matter exists, so while it's a fascinating idea, the wormhole theory is on very shaky ground. It's mathematically beautiful, but it seems physically impossible, at least for a black hole formed from a collapsing star. The singularity is not a gateway, but a dead end. But if somehow nature does allow for exotic matter, then the center of a black hole could be the most incredible doorway imaginable. Number 5, it's the source of a white hole. The mathematics of general relativity that describe an eternal black hole, one that has always existed, also describe a white hole. They are two sides of the same mathematical coin. While black holes are thought to be common in the universe, we have never observed a white hole. Some theories, like loop quantum gravity, suggest that a black hole could bounce and become a white hole in the very distant future. A gamma ray burst observed in 2006, GRB 60,614, had characteristics that some have speculatively linked to a white hole, though this is a very fringe idea. A white hole is the exact opposite of a black hole. A black hole is a region of space-time that you can enter, but you can't leave. A white hole is a region of space-time that you can leave, but you can't enter. Matter and light can only flow outwards from a white hole. It is a cosmic fountain, a place where things spew out into the universe in the purest mathematical solutions of general relativity for a non-rotating, uncharged black hole. The black hole and white hole are connected. The singularity of the black hole in the past is linked to the singularity of the white hole in the future. They are two ends of the same wormhole, but this is for a idealized eternal black hole. You know, what about a real black hole, one formed from a collapsing star? The idea here is that the singularity is not a stable final state. It's a temporary transitional phase. This is the core idea of the black hole bounce, predicted by some theories of quantum gravity like loop quantum gravity. In this scenario, a star collapses. The matter falls inward, crushing down toward a singularity. But just before a true singularity can form, quantum gravity effects take over, the collapse is halted and reverses. The black hole transforms into a white hole. This transformation might take an incredibly long time from our perspective outside the black hole due to extreme time dilation. It could take billions or trillions of years, but eventually the white hole would erupt. All the matter that ever fell into the original black hole would be violently ejected back into the universe. The information that seemed to be lost would be returned. The singularity is not a point of destruction, but a point of transformation, a cosmic pause button. It's where matter and space-time are held in a state of suspended animation before being reborn. If this is true, it means some of the most violent explosions we see in the cosmos, like some gamma-ray bursts, could theoretically be the death cries of ancient black holes, finally turning into white holes and releasing their contents. The singularity is not an end, but a violent delayed beginning. Number 4, it's a ball of exotic matter called a gravistar. The gravistar concept was proposed in 2001 by Powell Mazur and Emil Mottola. The name is short for gravitational vacuum star. Unlike a black hole, a gravistar would not have a singularity or an event horizon. It would have a solid core, a thin shell of matter, and a vacuum exterior. It would be almost indistinguishable from a black hole from the outside, but it would not produce Hawking radiation. This is another theory that gets rid of the singularity entirely. It's called the gravistar model. The idea is that just before an event horizon can form during the collapse of a star, something strange happens. The spacetime inside the collapsing star undergoes a phase transition, much like water turning to ice. This creates a bubble of what's called false vacuum, or dark energy. The result is a structure with 3 layers. At the very center is a core of this dark energy, which has a negative pressure. It pushes outward, resisting the pull of gravity. Surrounding this core is a very thin, very dense shell of normal, but highly compressed matter. Outside of that is the normal vacuum of space. From a distance, a gravistar would look almost exactly like a black hole. It would be incredibly dense and have a powerful gravitational pull. Light would be bent around it in the same way. But there are crucial differences. A gravistar does not have a singularity. The outward pushing dark energy core balances the inward pull of gravity, creating a stable object. And most importantly, a gravistar does not have an event horizon. There is no point of no return. There is just a physical surface, the thin shell of matter. It would be a black hole imposter. It would be incredibly difficult to tell the difference between a gravistar and a real black hole. One possible way would be to look for the gravitational waves produced when 2 of them merge. The signal from 2 merging gravistars should be slightly different from the signal of 2 merging black holes. As our gravitational wave detectors get more sensitive, we might be able to test this idea. The Gravistar model is a radical alternative. It says that black holes, as we imagine them with their singularities and event horizons, might not exist at all. Instead, the universe is populated by these ultra-compact balls of exotic energy, objects that mimic black holes but are governed by different and less problematic physics. Number 3, it's a ball of tangled strings. String theory posits that the fundamental constituents of reality are not point-like particles, but one-dimensional, vibrating strings. A typical string is thought to be on the order of the Planck length, 10 raised to the power of 35 meters. There are multiple versions of string theory, type I, type IIA, type IB, etc., which were unified in the mid-1990s into a single framework called M-theory. This idea comes from string theory, one of the leading candidates for a theory of everything. In string theory, the fundamental particles we see, electrons, quarks, photons, are not actually points. They are tiny vibrating one-dimensional strings. Different vibrations of these strings correspond to different particles. A certain vibration makes an electron. A different vibration makes a photon. Gravity is also included in this picture. One particular vibration of a string gives rise to the graviton, the hypothetical quantum particle of gravity. Because string theory is a quantum theory that includes gravity, it should be able to describe what happens at the center of a black hole without any infinities. So what does it say is there? The fuzzball theory proposed by Samir Mathur and others offers a picture. It says that when a star collapses, it doesn't form a singularity. Instead, as the matter gets more and more compressed, the strings that make up the matter and energy get tangled and merge. The entire region inside the event horizon becomes one giant, complex, vibrating object, a fuzzball. A fuzzball doesn't have a singularity. The energy is spread throughout the entire volume of the black hole, all the way out to the event horizon. It's not an empty space with a point at the center. The whole interior is filled with this tangled mess of strings. It also doesn't have a sharp, well-defined event horizon like in general relativity. The edge is fuzzy, hence the name. This solves the information paradox beautifully. When something falls into a fuzzball, its strings just get added to the larger tangle. The information is not lost, it's incorporated into the complex vibrational state of the entire fuzzball. When the fuzzball emits Hawking radiation, the radiation is not perfectly thermal or random. It contains subtle correlations that carry the information back out. The fuzzball is a quantum object. There isn't just one possible fuzzball for a black hole of a given mass. There are a huge number of possible string configurations, each corresponding to a different quantum state. From the outside, they all look the same, but on the inside, each one is a unique, information-rich quantum system. The singularity is replaced by a vast, complex, but ultimately understandable ball of strings. Number 2, it's a bouncing Planck star. A Planck star would have a density known as the Planck density, which is about 5.1 x 10 raised to the power of 96 kilograms per cubic meter. This is an unimaginably high number. The bounce of a Planck star would be very fast from the perspective of the matter itself, but due to extreme gravitational time dilation, it would take billions of years for an outside observer to see it happen. This idea comes from loop quantum gravity, but it focuses on a specific object. It's called a Planck star. It's another theory that relies on the idea that space-time is not infinitely divisible. There is a smallest possible length and a maximum possible density. Here is the life story of a Planck star. A massive star collapses under its own gravity. The matter falls inward and the density skyrockets. But the collapse doesn't continue to infinity. When the core of the collapsing star reaches the Planck density, the maximum density allowed by quantum gravity, the collapse is halted by an incredibly powerful outward pressure. This is the same quantum pressure from the granular nature of space-time we discussed before. What's left is a Planck star. It is an object that is incredibly small, much smaller than an atom, but it contains the entire mass of the original star. It's a tiny, ultra-compact object sitting at the center of the black hole's event horizon. But the Planck star is not a static object. The outward pressure is so immense that the star immediately bounces. It begins to expand, so the singularity is replaced by this bouncing core. The matter falls in, forms a Planck star, and immediately starts to fly back out. This is where time dilation comes in. For the matter itself, the entire process of collapse and bounce might take a fraction of a second. But for an observer far away from the black hole, time is running incredibly slowly. From our perspective, the bounce would take billions of years. A black hole that we see today, which might be billions of years old, could be, from the inside, in the middle of this incredibly fast bounce, stretched out over cosmic timescales for us. This means that a black hole is a temporary object. Eventually, the expanding Planck star will reach the event horizon. At that point, the black hole will die, and all the matter and information will be released back into the universe. This provides another solution to the information paradox. The singularity is not a permanent feature, but a momentary turning point in the life of matter, a bounce that is frozen in time from our point of view. Number 1, it's a point of infinite density. This is the classical singularity, the one predicted by Penrose and Hawking's singularity theorems in the 1960s. According to unmodified general relativity, if an object is compressed to within its Schwarzschild radius, the radius of its event horizon, its collapse to a singularity is inevitable. For the Earth to become a black hole, it would need to be compressed to the size of a sugar cube, about 9 millimeters in radius. For the Sun, the radius would be about 3 kilometers. We end where we began, with the original, terrifying, and beautifully simple answer given by Einstein's theory of general relativity. What is at the center of a black hole? A singularity, a point, a geometric location in spacetime with zero volume and infinite density. This is the theory that all the others are trying to replace. It is the default answer, the one that our best theory of gravity gives us if we take it at its word and follow its mathematics to their logical conclusion. In this view, when a star collapses, the matter is not just squeezed. It is annihilated. The individual particles that made up the star, the protons, neutrons, electrons, are crushed out of existence. All that remains is their mass, their charge, and their spin, properties that now belong to the black hole as a whole. The matter itself is gone, compressed into a point that is literally infinitely small. The curvature of space-time at this point is also infinite. This is not a metaphor. The equations of general relativity genuinely produce the value infinity. This is the point where the theory breaks down. It is not just that we don't know what happens, it is that the very concepts of space, time, and physical law cease to have any meaning. This classical singularity is the purest and most problematic of all the answers. It is pure because it is a direct consequence of our most elegant theory of gravity. It is problematic because it points to its own failure. It is a mathematical prediction that physics cannot describe. It suggests that at the heart of these massive, powerful objects is a hole in reality itself, a place where the universe as we know it simply ends. All the other theories we have explored, fuzzballs, Planck stars, wormholes, universe factories, are attempts to fix this problem. They are attempts to smooth over this infinity, to replace the breakdown of physics with new, more complete physics. But until we have a proven, tested theory of quantum gravity, the classical singularity remains. It is the ghost in the machine of general relativity, a constant reminder that, despite all we have learned over the past century, the universe still holds secrets that are beyond our grasp. It is the known unknown at the heart of the cosmic abyss.